Yes, sir, the thumbs up and
Sir, please mute all themselves.
yes, sir.
So Dr. Bhagwant Reddy correlated his subject well to his spiritual and philosophy and even to the vibrations of the brain and also to the virus, etc. It's nice. So now I'll start my topic. So my today's topic is nano concept, ion conductive polymeric materials, application to electrochemical cells. This is purely the research topic. So this a nano concept is a new topic, but it started 2 decades ago. So my idea is to give the some concept, that means some idea about the nanomaterials, about the research. So most of the I covered in this outline of the today's presentation is actually what is nano. So we every day we experience something like, because you see, say at our home, when our grandmother makes chutney, so that is different taste. At present, our ladies are making chutney, that is different. So everybody can be realize that, because what is the change between the grandmother's chutney and today's what our family members are making. So because earlier they used to grind proper way in the proper size, so that will give the taste of the chutney. But in present days, what we are using the mixer, maybe other electrical machines, etc., to grind it. So that maybe the proper, not in proper size as our grandmother made. So that means a lot of difference. That means size also makes a lot of difference. So that means size makes a lot of difference. So because of that in that materials also, when it's a bulk form or nano form, it's having the different properties. Because nano having a lot of merits when you compare the bulk. Okay, the second way what I cover is why and what makes difference when in nano size. Then I cover this various synthesis methods of nanometers, how to make the nanomaterials. Then also some of the techniques how to measure the size of the nano. Because earlier we don't know. We realized just 2 decades back, but it's not a new technique. Even the 4th century BC also some of the goals which they used to make the cup, so etc., by using the nano dispersion of nano into glasses. So that is not a new technique. But anyway, we realized the 2 decades back, because we have some experimental measurements to measure the size of the material. So that means we realized it. So then in the second part, I make use of that nanoparticles in ionic materials, ion conducting materials. So this is purely my research. So this is also two of my students are doing the research in synthesis of nanomaterial, and also 2 or 3 students are doing on the conductive polymer, nanocomposite polymer electrolytes. So one of my students awarded the degree in the ion conductive polymer electrolytes in 2019 from JNTUH. Okay, now we'll start. What is nano? So because we know the size, but we have to give the certain size as a nano. So you see that when the size nano means 10 to the power of 9 means 9 meters, everybody knows that. So 1 nanometer is equal to 1 10 to the power of minus 9 meters. That means all the nanometers are, that means all the materials which is under the given some dimension, define some dimension as a nano. So that is less than 100 nanometers, they define that as a nanometer, because less than 100 nanometers which have some benefits, some merits when you compare with the bulk materials. So because of that only they define the nanomaterial, that means nano means up to 1 to 100 nanometers, that material will define as a nano. That means in any one dimension, whether the x direction or y direction or z direction, but in any one dimension. So we call that as a nanomaterial. We know that what is science. That means whatever we study about that its object of the material, we call that as a science. But when it's coming to the technology, so that means when anything we're going for the application, first we have to design, then how do we have to characterize? First design, then characterization, then production. That means how to produce that. Then how to application for the devices, then how to control this. So this is called that as a technology, right? This is called nanotechnology. So classification of nanostructured materials. So just now I explained about the size of the nano. That means less than 100 nanometers. We call it as a nano. That means size as a nano. But behind that, we don't call it as a nano. So do you see that this is classified into 4 groups? One is 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional. So 1-dimensional means any 1 dimension. That means you take X direction, Z direction, Y, Z direction. In all the direction that is in less than 100 nanometers. That means all the directions in the nano size. We call it as a 0-dimension. So when 1 dimension, that means it any 1 dimension. That means the X direction or Y direction or Z direction. So that having the more than nano size. That means more than 100 nanometers. We call that as a 1-dimensional material. Where in the both that means if you take X, Y, Z direction in any 2 direction, so that is not in the nano size. That means that is more than 100 nanometers, maybe the micro or the water. So that we call that as a 2-dimensional. That means we are making the thin films. If you observe the plates of that, what we use for our solar cells, the thin coating will be there. These are the 2D film. That means it's a thin layer on that. We call that as a 2-dimensional. 3-dimensional means in all the directions, in X, Y, Z directions, it's more than 100 nanometers. That means it's in the bulk. So that we bulk, that's one bulk one. That means more than 100 nanometers also. That we call that as a 3D-dimensional nanometer. So this is about the classification of the nanomaterials. So coming to here, why the nanomaterials having the better property when it compares to the bulk. So what makes difference when in nano size? So you see here, if you take a cube of 1 meter, so its area is 6 meters square. If you break that into 6 pieces, 8 pieces, then that area is 12 meters square. If you break that into 27 pieces, that is 18 meters square. That means if breaking that into smaller size, the surface area increases. But value is same. Whatever the material we're taking for that 1 meter, 1 cubic meter, the value is same. But here the surface area increases. So like that, if you break into smaller sizes up to nano size, so about the surface area of that 1 meter cube we are taking, it's maybe the more than 1 lakh meter square area. So that means surface area to volume area is increasing. That means when you are breaking it to smaller size, so that surface area is increasing. That's the first property when you make that into nano size of any material. So you see here, so nanomaterials have a relatively larger surface area when compared to the same mass of material produced in a larger form. This can make material more chemical. That means when you're making it smaller, that means it makes chemical reactive. You see the example. You take the sugar in the crystal form and also that in the powder form. You put in it 2 different classes. So which one dissolve first? Whatever the powder you are keeping in that glass, so that dissolves fast, quick, because that is in smaller inside. That means that reaction will be very fast. So if it is crystal one, that takes longer time. So coming to that size, so whenever we construct houses, so what we'll do, we'll take the brick that having some size 4 into 8 inches. Why not bigger? Because that is suitable for that construction, that gives the strength. So that means size matters everywhere. Size matters whatever we are going for the application. Okay? So that means it's having the interface. That means connection between the 2 particles or 2 molecules, etc. That means it will be the greater. So that means that increases strength. Not only the strength, it also increases the electrical property also, even the magnetic properties. So that we'll discuss later. Okay? So that means you see here, even you take the ice, you make crush into that into smaller, then you put that into the glass, and also you put the ice cube. Which one dissolves first? So where we are putting the ice into crush, so that dissolves faster. So that means here side effects law. That means it reacts very fast. Okay? So second one, when you measure the energy gap of the material, when you reduce the size, you see here. So this is on x-axis is the size of the particle, and y-axis is the energy gap. You see here, but the size is decreasing, the energy gap is. So that means it's the quantum effect. We call that. You see here. Next one. slide. You see here, that the conduction band, here is the valence band. But this is the bulk material. You see here, the energy gap is very small. But you make that into smaller size, then you see that energy gap is increasing. Energy gap is that means decreasing in size, the energy band gap is increasing. So that means this is the second property, that is the whenever you make into smaller size, so that energy gap is decreasing. You see this? You see here, in small nanocrystal where the electron energy levels are not continuous because it's in a bulk, it's a continuous. But when coming to its narrow size, it's a discrete. So we call it as a quantum confinement. That means restricted to that electron, whatever that there is a movement of that restricted to some dimension. Okay, that we call it as a quantum confinement. You see here, these are the actually gold in yellowish color, but you make that into smaller size, less than 100 nanometers. The size, if you this is dispersed in some liquid, you see that the color is in the gold. That means the color is changing. Why the color is changing? Because you see here, so whenever that making into smaller pieces, sizes, then what happens is the band energy gap. Because of that, there's a change in the colors or whatever that. You see here, this cup, Lazarus cup, which is in the British Museum. So you see that this is made in the 4th century BC. It's not yet the new. That means it's not a new technique. Even that 4th century BC also they used this technique, but they have not realized because of this nano size. That they realized, but it's not nano. They have not realized its size, whether scientists or what. So then they dispose in the glass. Then you see here. So when it reflects back the light, then this color is in greenish. So when it's transmitted, that we put a light inside the transmitter, that's in reddish in color. So that means what? So this is not a new technology, but we realize because we have the equipment to the devices to measure the size. So you see here, the properties of materials can be different at the nanoscale and also for two main reasons. So one is the surface area, second one is quantum confinement. That means the phase where energy gap is increasing when you make into smaller sizes. Okay. So coming to here that the properties are different when you compare with the bulk materials. So optical properties. You see the optical properties are different, you make that into a smaller size. When electrical property, increasing conductivity, you see that when you make that carbon into that carbon tubes, that in the nano size, so that conductivity is 6 orders more even the copper material. That is 10 to the power of 6 times more even the copper material. That means you see that even the carbon which we are making that into smaller size in the nanotube form, which is having high conductivity even the copper. So same way the magnetic property also increasing. So mechanical properties also increase. That means the hardness also increasing when you make this any device, anything with this nanoparticle, the hardness of that strength of that material is chemical properties. So increasing its reactivity. That means just now I give an example how the sugar crystal, how the change in the sugar powder. Because that sugar powder dissolves very fast. Because of what? The chemical reaction is very fast with that, within that water. But in the crystal form that takes longer time because of that size. So that various synthesis methods of nanomaterials. Okay, so up to now I have given the why, what is the size of the nano, why, what is the makes difference. The difference is what? When the difference we compare with the bulk and also nano size, that is the smaller size, the difference is only in the surface area and also quantum confinement. That is quantum effect. So because of these two, the properties are totally different. The properties are totally different. But we should know the synthesis process also. Okay. So preparation of nanomaterials, these are in two ways. One is a physical method, another one is a chemical method. Physical method, it's a top-down approach. That means you take the bulk material, you see here, you take the bulk material that break into small, so by grinding or vibrating machine or maybe using some physical method. So then we make the nanoparticle. That means we are making that into simply crushing it. Then we are making it a smaller size. That we call that as a physical method, the top down. That means we are taking the material, bulk material as a top. Then we are making that into smaller size. So that becomes into powder. So that is called top-down approach. So chemical method, bottom approach. So that means we are making combining atom to atom, then making the cluster. Then we are making that as a nanoparticle. That means this by using by chemical methods. That means some sort of chemical reaction is taking place in this. Then the particles, that means we can make the nanoparticles. So when you compare with physical and chemical methods, so chemical methods are having this more and more merits, because when you use the chemical method, we can make that material whatever size we require, whatever the shape we require, by maintaining the environmental condition like maintaining the pH, temperature, pressure, etc. So that means this is the chemical method is better method when you make use of the physical method. That means chemical method by using the chemical reaction. So by maintaining the environmental conditions like temperature, pressure, pH value, then we make that into the size what we require, what technology people require. Because for that application, we need some application for certain size. So that means that the chemical methods are very much useful for us. That means we can make the different whatever the size we require. But in the physical method, it's difficult to know the structure because it's maybe this crystal structure also may be damaged when we use the physical method because we are crushing it. So that means there is also changes in the property also. So, but chemical methods by using what? But bottom approach. That means we are starting from the bottom level by using the chemical reaction. So, the top-down approach. So there are you see here. So top-down approach. That means the bulk material and makes it smaller, thus breaking up larger particles by the use of physical process like crushing, milling, or grinding. These are not suitable for preparing uniformly shaped image because it's not in the perfect shape because the different particles may be in different shape. So the biggest problem is that imperfection in the surface structure because we are crushing it. The surface structure is imperfection. That means it damages it, the crystallographic structure. Because it's a top, simply we are crushing, we are using some force, some energy on that to make the smaller into smaller sizes. So these are the methods like attribution, ball milling. That means you see here, this one where you're putting some balls, you're putting that bulk material in this, then simply you're rotating this one, what happens? This balls crushes that material. Then we'll make that material into smaller size. You see here, this one simply we are vibrating or crushing it. Then what happens? You are keeping some material between this, then what happens? This you will make smaller into smaller size. So we can make any material into smaller sizes by taking the material and grinding it or crushing it. So this is the physical method. So sputtering and evaporation is also there. That means you take the material as it is and simply heat it. Then what happens? That material will be melted, then it's boiled, then next stage is what? Vaporization. That means if you correct the vapors on any substrate, that means what? Over that solar cells we are making, they are coating on the glass. So the thin layers by using the thermal evaporation or maybe sputtering, etc. So sputtering means what? Where we use some material, then we use maybe the electron beam or the ion beam, etc. So when this hit that, then when we hit that, then what happens? These may be atoms or the molecules will be ejected from that. Then we collect on any substrate, we coat on a substrate. That means these are very much useful for to make a thin film that we can coat on any substrate. Okay, this is the physical methods. So bottom approach. So that means we are making that as atom by atom or the molecule by molecule or cluster by cluster. So that means we can generate by using these methods in a proper uniform size or shape and its proper distribution of its size, etc. So even you control that reaction, even we can control that reaction also. So that means we can make that whatever the particles we want to make. So that maybe in proper size we can make, proper shape we can make. So that means whatever we require we can make. Okay. So that means one or two techniques I'll give you here. So sol-gel technique. It's a very easy technique. It's like a chemical method. So whatever you want to make, you want to make a silica oxide, SiO2. Then you take the tetrahydroxylene TMOS and tetrathiaxylene. So you dissolve some solvent, then it forms some shell. So that way here the process are hydrolysis, condensation, and growth of the particle. You see this flow chart. So where we are dissolving it and hydrolysis method is forming, we are adding something, then it's a condensation, then it forms the gel. So where that gel we are drying it. So when we are drying it, when the evaporation is drying, supercritical drying, so it forms aerogel and xerogel. So xerogel is nothing but is a solid formed from a gel by drying with unhindered shrinkage of xerogel, which gel retain high porosity, 15 to 80%, and enormous surface area. That means whatever you are making, that becomes a nanomaterial. So that means final compound will get aerosol. Is a synthetic porous ultra light material derived from the gel in which the liquid component for the gel has been replaced with a gas. So the result is a solid material. So this is called sol gel method. So that means the chemical reaction is taking place here. So chemical reaction is taking place, it forms that. Then where we are gel, we are drying it, that means we are operating the solvent, and finally we dry in the furnace, etc. Then finally we will get the material. So that means here we have to maintain some sort of pH and also some sort of temperature and also pressure, etc. So then we can make that material whatever the size we require. That means we maintain certain pH 9, then maybe we're getting maybe 20 to 30 nanometers. We change the pH value, maybe that may be changed to the 40 50 nanometer size. So that means by controlling pH and temperature, we can make the material whatever the size we require. So coming to the next one is chemical reaction. That one is chemical precipitation method. So that means the preparation, reaction, end product separation. These are the 4 processes. You see here the example of U34 nanoparticles, where you are taking these 2 FeCl36H2O and FeCl24H2O. So these we are dissolving in the water, where we are adding in sodium hydroxide, which to maintain the pH value. Then where the reaction is taking place, then it's formed Fe3O4. So here the Fe3O4 nanoparticles synthesis process. So that we can make the Fe3O4 nanoparticles. So this we finally will, this all will be in the environment of nitrogen, because if you will use another in the ordinary environment, so there is a contamination there. If you use in nitrogen environment, there is no contamination, then we'll make that particular Fe3O4 within some sort of purity, will get about 99. Over 90% purity. So that means after that, so after making this end product, then we separation. That means we can use the separation method by washing with the 1.01 mole HCl and neutralizing it anionic charge on the nanoparticle side. Then we are using particle particles who are separated by centrifugation. By centrifugation method, we use separate it. Then we simply dry it. Then we get the Fe3O4. So you see here, what maintained the pH 9 will get the size of this nanoparticle is 40 nanometers. Then if you change its pH value, then automatically the change of that size will change. Even what I used in this, I prepared this Fe3O4 nanoparticles, so where that pH 9 is a spherical shape nanoparticles are prepared. So these are having the 20 nanometers size, less than 20 nanometers size. So electrochemical deposition. You see here. So if you want to make the any metal nanoparticle, simply you take this, which is having some source of that metal of that liquid, then simply apply some current. Then what happens? Where that metals are there, which is having the positive charge, that moves towards the cathode side. That means this metal will be deposited on the cathode side. Simply collect that metal from the cathode, then we'll get that the of that material. That means that the metal. So that means it's called that electrochemical deposition. That means it's a chemical process. That means electrochemical, which are using that some electricity, some current here. So electrolysis process taking place within this liquid. When you apply current, then this nanoparticles of that metal. If you want to make the titanium, you use the whatever the source is there within the titanium, that solid. You take in this, then this titanium will move towards the cathode side. Then simply collect from this cathode, so that material will be in the form of nano size. So you can make that with any metal like copper, platinum, nickel, gold, etc. So nanotube growth. That if you want the tubes, so just now I have given explained in the properties, when the properties of the nanotube of the carbon, which is having the conductivity of 10 to the power of 6 times. The 6 sort of higher conductivity even the copper material. So that is because of the size of that material. So to make that, we use arc discharge method. So in these two carbon radioactives will be used. In this, when you apply this high current, then what happens? So the current creates discharge and vaporize the surface of one carbon. That means the vaporizes the carbon, then that vapor will be coated on another electrode. Simply collect that from the collect that electrode, so that material will be in the form of nanotubes. So this is called arc discharge method, laser method. That means in this case we are using some current, we are applying that. So in this case, laser we are using. That means laser beam will use. Then what happens? The laser ablation. That means what laser hit that, then that material may be ejected from that. That may be coated on some substrate. So that substrate we collect that from that material. So that will be the nano size. So in that we generally use some catalyst. So that's cobalt, nickel, etc. This will use around 12 degrees centigrade. So by varying temperature, the catalyst composition, other parameter, the nanotube diameter and size can be varied. That depends upon the catalyst and environment, the temperature, the size of the diameter of that tube is also changing. That means you can change the size while maintaining the environment of that. That means the temperature, even the catalyst. Okay. So this up to now I have given the some of the methods, because the number of methods are there to make the nanomaterials, even the physical method and also chemical methods. But I have given some of the methods to get the idea about the nanomaterial synthesis process. Now I give you the idea about the techniques. What are the techniques are available to determine the size? Because we don't know what the size of that material which are making. To measure that, we need some technique. Some that means some methods. So in that, generally we use, because other methods also there, like neutron scattering and different type of methods are there, small angle X-ray, etc. But here I'm giving the most of the methods we are using to characterize that, to find the size of that, because these are the available in the most of the laboratories. So remaining things are not available in most of the laboratories. Maybe even in India also not available in some of the techniques. Okay, so X-ray diffraction method, scanning electron microscopy, transmitting electron microscopy. So these are available in most of the labs, in the most of the universities and labs. Okay. So X-ray diffraction method, everybody knows that this X-ray diffraction method, but it follows what? Brown's law. 2d sin theta equal to n lambda. That is the Brown's law. Okay. So based on that, we record that spectrum. That means when X-rays hits, when we record that diffraction pattern, so we'll find the peaks, various peaks in that. Okay. So how to measure it? The formula is D is equal to K lambda by beta cos theta. So most of us know that, so researchers know that. So when we keep that sample in the X-ray, then with diffraction taking place, we record it. So now we're recording, earlier they used to record on the films, but we are recording directly to the interface to the system. We'll get those spectra. Then you take that, there will be number of, if it is the crystal nature, we'll get the number of. If it is some of us, it will not get, because where is the particular arrangement of atom is, or molecules are there, then only the diffraction will take place with that. So D is equal to K lambda is the beta sin theta is the formula to measure the size of that particle, size of that material, where beta is the full width of half maxima. Full width, that means we take full width at half maxima. You take it half maxima, that width of that will be the beta. So theta, this is the theta angle and the x-axis. So where lambda is the wavelength, what wavelength of that X-ray we use, that is the lambda, then K is the constant of that instrument what we use for that. So in general, that value is 0.9. So when you substitute that in this formula, we'll get the size of that nanoparticle. So other method is scanning electron microscopy. So this you see here, where we'll put the sample here. So where we can record the scattered electrons from here. That means we send the electrons, then we record it. So this gives the three-dimensional pattern. So you see here the electron microscope that produces image of a sample by scanning the surface with a focused beam of electrons, and electron interact with atom, the sample producing various signals. So that contain information about the surface topography and composition of the sample. That means But the electron beam we are using whatever the scatter from that we are recording. So that means that we get from the image, like image. So its image is like a three-dimensional. You see this, this. So this image for the virus, where it's in smaller size, difficult to find. So that means it's difficult to find. We know where is that virus because of that one we are using mask, etc. So this is about the size of the bacteria. So that means we can measure by using this scanning electron microscopy what of the size of that, what of the structure of that. So which gives the three-dimensional. You see this is the three-dimensional picture. This is the two picture. So we can record both the ways, the transmitted beam and also diffracted beam. So that means simply we are using that electron beam in this case also. Electrons made to pass through the specimen and image is formed on the fluorescent screen either by using the transmitted beam or by using the diffracted beam. You see here. So electron source is here. Simply the lenses are arranged. We are putting our sample here. Then our screen is here. So that means we are recording simply the transmitted beam in this case. So this we call that the transmission electron because high resolution microscope. Whatever you are using, scanning electron microscopy and also transmission electron microscope, these are the high resolution microscope. In our laboratories also, but when biology laboratory, zoology laboratories also there some microscope. So those are not high resolution microscopes. These are the high resolution microscopes. You see here, this is the virus. So these are the bacteria of that. So here we are getting the two-dimensional picture. So in that case, we are getting what three-dimensional. That means we can see that in three-dimensional way of this virus. But coming to here, the transmitter could this records the two-dimensional. This also bacteria is also two-dimensional. So the Fe34 nanoparticles, what we create, you see here that is the nearly 20 nanometers. You see here the 100 nanometer size of this. So that is around whatever we prepared that the 20 nanometer size of the nanometer. So that means it's a spherical one. That means by using this transmission electron microscopy, we can find its size and also shape also even with the scanning electron microscopy also. So these are the high resolution microscope. So we can measure the size of the nanoparticle. So that means once we know the size of this, so we can find its properties also. What are its benefited to us when you compare with the bulk. So you see here the comparison of the SEM, that means scanning electron microscopy, and also transmission electron microscopy. So here the size of the bacteria. So here the size of the bacteria of that single one, that is the transmission electron microscopy. So far I have given the idea of the nano. So what is that concept? Why these are the useful? Because these are having the better and better in the properties when you compare with the bulk materials. Because of that surface area, so where it's having the chemical reaction, where it can disperse easily in any material. Any material. If you want to disperse as a film size, it's very easy, you can disperse. Even nowadays, they are using the paint. They are saying something, it's like dust proof, etc. Because they are using some sort of technique to making it too small, the smaller size. Even that you can put in this larger area because that we are making it smaller size. So that means we can make the dust feel like that. So they are saying by using this technique only. Okay. So nano composite, because this is also my research paper. So I published number of papers on this in reputed journals. So some of my students also working. In 2019, one of the students submitted my thesis in the blending of two polymer electrodes and studying its properties. So here I'm giving the idea of that. What is ion conducting polymer materials? The solid material which is having high conductivity, which is having high ionic conductivity, we call that as the fast ion conductors or super ion conductors or solid electrolytes. So based on that microstructure, these are classified into number, that's the glasses, composites, crystalline or polycrystalline materials, polymerics, etc. So that means all these are having high conductivity. So we call these are as a fast ion conductors or maybe the super ion conductors or solid electrolytes. Okay. So these we call it as a ion conductors. Okay. So what is polymer ion conductors? So that means we take any polymer, you add some ionic salt to that, make that into some composition, then that measures its conductivity, which is will have high conductivity. Then we call it as the solid electrolyte or electrolyte. You see here in this case where that PuO is there, that PuO structure is CH2, CH2O, CH2, CH2O. This is the chain of that PuO where oxygen is there. When you dissolve that, that means when you dissolve this PuO and also lithium salt in some solvent and you mix it, then you dry it, you will get some material where in that PuO this oxygen is there, this oxygen having the lone pair of electrons, so which interacts with, that means it interacts with the lithium cation, that means where this lithium chloride will be dissociated, so chlorine will be separated, so lithium will be interact with this, that means this coordinate with the oxygen. Okay, so this is called the polymer electrolyte. That means it's having high conductivity. So that means there is the advantage of solid electrolytes be compared with the liquid electrolyte. So because the liquid electrolyte, there is a possibility of leakage, etc. So in that case, we are using solid electrolytes because in the most of our mobiles, etc., we are using solid electrolytes. But in your inverters, etc., at our home or the offices, so where the batteries are there, it's larger size. So these are the liquid electrolytes we are using. But in our cell mobiles and with the dry cell, these are of solid polymer electrolytes, where we use the two electrodes in between solid polymer. We call that as a separator. This acts as a medium where that ion can mobile from this to separator. When you charge, this will move towards the other side. When you discharge the perimeter use of it, then this ions will move towards the other side. That means your charging, discharging will take place in this case. Okay? So this is about the solid electrolytes. Where advantages of the solid electrolytes, easy to prepare as a thin film, whatever sizes we require. So these are also having mechanically stable material we can make. Also having high ion transport, that means high ionic conductivity, and also where the ability to contact with the electrode, because this electrode should contact with the two electrodes. So that means compatibility is excellent when you use the solid polymerics as a polymeric material, because most of the cells we are using the batteries which is having the high efficiency now. They are using the lithium ion polymer batteries. In the technique, lithium ion polymer batteries. That means where that the solid material is there, that's the lithium ion polymer, where the other sides are using lithium. So one electrode, one other is the cathode, the combination of lithium and some. So here I will explain, I will give you the picture about the solid separator, that means solid electrolyte. So these are having the application to electrochemical battery, that means the batteries. So electron sensors we can make by using this capacitor, we can make VLCell, we can make some sort of memory devices making by using this solid electrolyte. That's the solid polymer. So why nano in ion conducting polymers? Because I have given the picture about the what is ion conducting polymer. So, but what the concept of nano I included in this ion conducting polymers. So you see here. So when we are making that to improve the conductivity of that polymer electrolyte, we are adding some salt, ionic salt, so like LiCl4 or LiPF6, etc. So then what happens is can accommodate some amount of the composition of the salt. So you further, if you want to increase, then the formation of ion film, that means again aggregation of the film. That again the salt is forming in that film. So even that inhibits that means that stops that mobility of those ions. That means decreases its conductivity. You see here. So when you started with 5, 10, 15, 20% of magnesium salt, its conductivity is increasing. Up to the 15% of that magnesium salt conductivity increases. But again, it's decreasing because of what? Where that ion pairing, that means again magnesium and chloride is forming together. That means cation and anion coming together and forming the pair. That means again aggregation of salt is taking place. So then what happens that the decreases conductivity. That means its utility is also decreases. So that means because of what? Ion pair. You see here, I have drawn the graph between the ion pairs. See here, whenever we increase the salt, so ion pair formation is increased. So because of that, its conductivity is also decreased. So to to improve that characteristics of that ion pairing, to dissociate more and more ions. So even nano also making, we are using that method. So you see here, ion pair is decreased with increasing Fe per nanoparticle. You see here, if you inserted, when you incorporated Fe3O4 in lithium solid polymetallic and magnesium polymetallic, etc., where you see here. So this is the where the salt with the polymer. Okay, so that means where this the formation of lithium with the chlorine. Here is the formation of the free chlorine as ClO4. So that means when this is increasing with the increasing of the salt. But when we added Fe3 nanoparticle, so then ion pair formation is decreased. So the Fe3O particle is added, so the ion pair formation is decreased. So that means what? When ion pair formation is decreasing, means automatically the conductivity is also increasing. Even this nanoparticle increases the strength of the solid polymetallic film. So it's a see here. So with the structure of that, where this the nanoparticle Fe3O4 incorporated in the solid polymetallic, where this is about the lithium ion, this is about the ClO4 or cation, this is the cation, this is the anion. So where these cations are there, where the lithium or magnesium, these also interact with the Fe3O4 not because this is the oxygen is there in this also. So where this will interact with this, they forming the network even with the nanoparticle, where it is also forming the network with the polymer. So that means this gives the more and more strength if you add the nanoparticle to the solid particle. You see here, so here the crystallization, here is the enhancements of conductivity. So that means even in decreases the crystalline nature of the polymer because crystalline nature inhibits the conductivity. That means crystalline nature is decreases the conductivity of that. If you increase amorphous nature, then that easy to move mobile ions. So that increase the amorphous nature. So we are incorporated in nanoparticle. So then what happens that decreases the amorphous nature, then conductivity increases. Okay. So this is also silica, some sort of silica, mesoporous silica, which is the nano size. So which is having some sort of channels in that. So where that lithium is also inserted, that means that penetrated in the channels, so that will coordinate with the oxygen of that silica. So that means this is also some sort of the structure of that when we add some lithium salt and also some sort of oxide material from the nano size to the polymer, where that it gives some strength to the solid polymer. So synthesis of nanocomposite ion conducting polymer films. So how to synthesize this nanopolymer films? See here. So polymer, we take the polymer in salt and nano. We separate because we dissolve this in separate solvent. Then we add this into the one beaker. Then we start for this. Polymer will dissolve for 12 hours to dissolve it. Then also we dissolve the salt in a separate beaker. We use by using solvent like PHF, that means tetrahydrofuran, maybe methanol or acetonitrile, etc. So that solvents you can dissolve the polymer in those any solvent. Then you start for few hours. Then that forms the homogeneous solution. Then in the same way you add some salt to the another beaker, you dissolve it. Then again you add some nanoparticles of whatever the composition we required, dissolve it. Then you mix that both the solutions in that. Then you start for a few hours. Then simply you take that mixture and pour into some sort of dishes. So polypropylene dishes or petri dishes of plastic or the glass. So then you dry it room temperature for few days or few days. Then you will get a freestanding film like this. This is the film what we prepared in our laboratory. So that means it's a simple technique and very easy technique. Other techniques are there, but it's a very simple technique. You can make it a uniform thickness of the film. By using this, we call it a solution casting method. That means simply you are taking that solution, that mixture, we are casting into some dishes, simply evaporating. Then we finally will get the film. So this we call that as a solution casting process. Okay. So once we prepare it, we have to characterize that. So what about the characteristics of those material? Okay. So for that we can adopted the number of techniques. So I adopted this in this research. My students are adopting these techniques: X-ray diffraction, data we are recording, and also scanning through microscopic data also recording, IR data recording, DSC, differential scanning calorimetry, thermal analysis method, and also conductivity methods we are using. So X-ray diffraction data. We know that we can find the crystal structure by using the X-ray diffraction spectrum. Okay, you see here in that A, where this is the further related to the polymer ethylene oxide, that is the polymer 1, so which is having the peaks, which showing it's not perfect crystal, but it's semi-crystal in nature. So when you add some salt, then this peaks are decreasing. That means what? Its crystal nature is decreasing. Even its broadening is taking place. That means this is about polymer with lithium salt. Then this we added some sort of nanoparticle to that. Then what happens? The size of this, intensity of this is decreased. Even it's broadening. So that means what is whatever we added nanoparticle to that, in what is the crystal nature. That it is in the amorphous nature of that. So its amorphous nature is required for the mobility. That means about the movement of ions. Okay. So that means what? Whenever we added that, so its the intensity is decreased. That means its crystal nature is decreased. That means it's widening. That means some of its nature is increasing, crystal nature is decreasing. Okay. So this is about the explanation for about the spectrum what is given here. So this is for another system where you added some sort of silica which is having the mesoporous size. Okay, so here is also having the pure PU is the lithium. Then we added this. Then what's happening is decreasing its intensity, simply broadening of this. So that is what its crystal nature is decreasing. So here is also the extract pattern of that from MCM41 is which is we are taking silica having this X-ray pattern. See that when we added to that polymer, this structure of the MCM41 is also disrupted because of there is interaction of that lithium ion with the silicon oxide. So where that interaction is good, automatically that the structure of the MCM41 also some sort of distortion will be there. So because of its structure is also some sort of changes that's taking place of that silicon oxide also. So SEM images. That means we can find its structure, the surface structure. Here it gives the surface structure of that film. You see here, this for the pure PUO. It looks like a rough. So that means roughness means it shows the crystal nature of that material. So when we added some sort of the salt, so this toughness is become smoothness. So that means what? Very disrupting it's the crystal nature. That means the crystalline structure, it increasing its amorphous nature. That means disorder is taking place within that. So if disorder is taking means there we can find some sort of wide space to move the ions. Okay. So that means when we added the lithium salt to that, then its smoothness is coming. That means its amorphous nature is increasing. So to this, we added some sort of nanoparticles, that is Fe3O4 nanoparticles added to this. Then what happened? These are dispersed in this film. So this dispersed. So even we increase the concentration of that, the aggregation of that nanoparticle is also taking place. So that means this can accommodate up to particular composition of that nanoparticle. So behind that, what happens? The aggregation of nanoparticle will take place. That means again it spoils the film. That means mechanical strength also decreases. That means it can accommodate up to particular composition of the nanoparticle. So this also for the MCM, that means another silica oxide is above one is for Fe3O4 nanoparticles which we added. This also for MCM, that means silica oxide mesoporous material which is also in the nano side. So you see here, this is the rough surface is taking place, where its smoothness is coming here when we added salt. So when further we added MCM41, that means silica oxide to this. So finally, you see this higher composition of that silica oxide, but its aggregation is taking place. That means again the separation is taking place of that silica oxide. So that means damage is the strength of that film. So that means it can accommodate up to particular composition of that silica oxide. You see here, this is also silica oxide, one type of silica oxide where we added. You see here, this for the pure PuO, for the lithium salt. So this is again the higher composition, so aggregation is taking place. So that means we can see that different domains in that. That means PuO lithium domain and also PuO with the interaction with the nanoparticle and also lithium also interacting with nanoparticle. We can see that by measuring the DS studies. Here is the differential scanning calorimetry. We can record thermic and exothermic also by using this endothermic graph. So when we recorded this, you see here, we can find that where it's having some sort of melting temperature. That means this crystal PuO melts here itself, which is having a temperature around 67 or 68, around 70 degrees C. So when we added salt, so this area is decreasing. That means this crystal nature is also decreasing. When we added this to the lithium salt, then what about this total area is decreasing? That means this crystal nature is decreasing. So this area gives the crystalline nature of that. So here you see it goes on increasing the Fe3O4 nanoparticle to like this. Then what happens is the area is decreasing. That means crystal nature is disrupted here. You see here the graph here between crystallinity versus nanoparticle. So at 0 here the crystal nature of that is around 34% of this. And we increase the Fe3O content, it's decreasing the crystallinity. But again, it is increasing because you see that when we have observed that this aggregation is taking place. Aggregation is taking place. So that means again the separation of that nanoparticle from the polymer taking place. So that means again the crystallinity is increasing. So that means the stability of that material will be high. That means mechanical strength will be high because it can accommodate up to this composition. So behind that, what's happening? Separation is taking place. That means mechanical strength will be decreased. So this is for the crystallization. That means while cooling, so crystallizes the material. That means while cooling, this is for heating. When it melts, that finding the melting temperature here, where the crystallizes at this temperature. So that means when we added the Fe3O4, the crystallization temperature is a little bit increased. But if you added to this lithium, then crystallization temperature is decreased. But when you added to this Fe2 nanoparticles, so in all the cases, this is the decrease. Even the crystallization area is also decreasing. That means what? It's disrupting its crystal nature. Even it's decreasing with the crystallization temperature also. But you see here at the higher concentration, again it is decreasing its crystallization temperature. So that means what? Where the separation is taking place. So because of that, because of that, this crystallization temperature is increased. So this is the annual temperature that we had annual at particular temperature, and again we measured it. Then this is about the composition of. You can measure the stability of that. You see here, where this is the PuLi for lithium, where its stability is increased when we add to that. This is about the lithium where the stability is decreased. So that means stability is also increasing when we add the lithium, we add the nanoparticles. That is the main concept, introducing the nanoparticles in this solid form electrolytes. So this is about the DSC cause of silica oxide material of MCM41 and SBA15. These are the crystallinity of decrease, how that is decreased when we increase in the concentration of silica oxide. So I add data. So here what happens when we study that, because various modes are there. You see here this in this CH2 CH2O, where this is related to the CH mode of that stretching mode of that PuO. You see here A graph for the pure PuO. So where this B is for we adding some salt to this, where we adding some sort of nanoparticle to this. So this is modified. The spectra is modified. This in this region it's modified. That means where that interaction is taking place between the polymer structure and also for the lithium, where the cation is there, where the nanoparticles there. So that means there is a forming a very good network between these three components, which is giving the strength to that material. So this is also for where we can see the CH2, CH2O, which we call it the COC stretching band, where that is also modifying this for the PU, this for PU, then PU. Then we added some salt and also nanoparticle to this modified. That means there is the structural changes are taking place within that polymer. So where that is interacting, that means forming the network, that means the coordination is taking place between the cations and polymer and also nanoparticles. Okay, this is our explanation for that. So this is how we can studied how the ion pair is forming, how that is decreasing with increasing. That means how the free ions are increased when we increasing the nanoparticles. You see here, free ions are increased. That means there is more and more lithium ion can mobile. That means cation can mobile. So which gives the more and more transport property. That is conductivity property. Conductivity property, right? Okay. So this is also about the ion spectra of silica oxide doped in the PO and lithium salt. So this also gives the similar trend in that. That means where the network is forming when we dope with the lithium salt and also the nanoparticles to that. Okay. So conductivity. So we measure the conductivity. The formula is to measure sigma is equal to 1 by RB, I by T by A. RB is the bulk resistance. We can measure with the DC measured method. RE is equal to V is equal to IR method in the Ohm's law. So what that we can measure that RB value. So then T is the thickness of that, A is the area of the sample. So then you can measure the temperature, that the temperature, see here, measure the conductivity with various temperatures. So in this case, A and B, so which is at 25 degrees C, B at 30 degrees C, you see here. So whenever we added to Fe3O4 to that, PuO lithium electrolyte, so the conductivity is increased. So you see here around 6 order, it increases it to about the 5 order. That means 10 times of the conductivity is increased when we add nanoparticle to that. So that means it's not only increased the nano concept, its strength, it also increased its transport property of the cation, which is very much useful for the application into any device like solid state. Conductivity versus how we
Excuse me, sir. Excuse me, sir. మీ వాయిస్ రావట్లేదు సార్. Hello. Sir, are you okay? Sir, his connection is good. Please be online, all the participants. సార్ ఏమైనా ప్రాబ్లం ఏంటి సార్? అంటే వాయిస్ రావట్లేదు. ఓకే ఓకే రైట్ సార్. జస్ట్ రైట్ సార్. Please wait all the participants. Unfortunately, the net disconnected of the speaker. Please wait. He is joining again and continue the session. We'll continue the session. Thank you, sir. Namaskaram, sir. Srinivas sir.
Okay, Uday. I am on.
Sir, అంటే సెషన్ అయిన తర్వాత కొంచెం మీరు బ్రీఫ్ ఇంట్రడక్షన్ ఇవ్వండి సార్.
No, it won't be good. I'm hearing it is a very quite interesting topic,
Okay, nice.
Nano Material. Yeah, it's quite interesting. I appreciate you.
Okay, thank you. Just he joined, sir. He joined in. Gopal.
Yeah. I know that there is some. Yeah, he's online only. Yeah.
Yes, sir. Sir, Gopal Reddy, sir, please continue. Jaipal Reddy, sir.
another material is for the PULS or samarium oxide we used here. So this panel we have this whatever we have prepared this solid ion conducting material is used as a separator, that means as a solid electrolyte. So we can make that as a solid batteries. We see here where the center the separator is there, the solid electrolyte is there. In this, we make use whatever the materials we prepared, we fabricated number of cells in that. So we achieved the good result in that. So where we use some sort of metal, that like if in case of sodium, we use the sodium metal as the electrode. In the case of magnesium, we use some of the magnesium electrodes. So cathode, we use some sort of compositions of iodine, carbon, and other materials used. Then we fabricate number of batteries. So here I'm giving the one. The we dope PU magnesium chloride to that, which has C. Hello. Hello. Can you hear me?
Yes, sir.
The network problem, which is sorry for that. Okay.
Yes, sir.
Okay,
It is audible.
Okay. Anyway, I'll conclude it. Okay. So that means you see here. So whenever we dope, that means we added some nanoparticle to this, its stability is increasing on that battery also. So that means where it's that nanoparticle which is in smaller size, so that disperses in the film, because that film is a very thin size, less than 100 micrometers. So that you can disperse these nano-sized materials easily within this material, which is giving the better strength, mechanical strength, and also it is in the ionic nature is also increasing. Then its battery stability is also increasing. So because of that, we use the nano concept in this polymer electrolytes. Okay, finally, I conclude this. Having some problem with system. Okay. So anyway, I conclude this. Having some PowerPoint is having some problems not moving. Hello. Hello.
Sir, continue చేయండి సార్.
ఇక్కడ PowerPoint ఏదో ప్రాబ్లం వచ్చింది. సరేలే కంక్లూడ్ చేసేస్తాను.
ఓకే రైట్.
So anyway, so in this session I have given the what is the main concept of nano. So that means what about the size effect? What are the difference between the bulk material and nano material? So that means when you compare with the size, so size always matters. In any aspects when you make cooking and whatever it may be, because when you make chutney at our home, so when the size also matters. So when you make a particular size, the taste will be different. In the same way, here is also having some merits when you compare the bulk, because if you make the smaller size, its mechanical strength or electrical properties or magnetic properties, all the properties are in. So only because of the two reasons, one is the surface area, another one is the changing the energy of where the quantum effect is taking place. So taking that into consideration, we added some nanomaterials to the solid materials where that improves strength as well as its transport property, and also its battery strength also increased. Because of that, we added that. We have used the nano concept in this problem. Okay, thank you. It's having some problem with this.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Any questions?
Sir, any questions from all the participants, students and faculty? English or Telugu, any language?
English, Hindi, Telugu, no problem.
నమస్తే సార్, భగవంత్ రెడ్డి సార్. నేను
భగవంత్ రెడ్డి చెప్పు. Yes.
సార్ మంచి ట్రాక్ సార్, మంచి ప్రెజెంటేషన్ సార్. అసలు అంటే బేసిక్స్ నుంచి స్టార్ట్ అయిపోయి మీ రీసెర్చ్ అంతా కూడా కవర్ చేసి చాలా మంచిగా ఉంది సార్.
మేజర్ పార్ట్ ఆఫ్ కవర్ మై రీసెర్చ్.
అదే సార్. ఇంకోటి సార్, అంటే ఇది ఇలాంటి ల్యాబ్ మన దగ్గర వచ్చి అంటే ఇప్పుడు చేయడానికి అవకాశం ఉంటుంది అంటారా సార్ మన క్యాంపస్ లోనే? అంటే ఇది నాకు తెలిసి చాలా వరకు ఉస్మానియా యూనివర్సిటీ అనుకుంటా సార్ రీసెర్చ్ ఇది.
Nano Material we can prepare anywhere in our laboratory also, no problem. We can prepare, but only for characterization we have to go to the laboratory, other laboratories. We can do that.
అంటే నా ఇంట్రెస్ట్ అయితే అంటే ఆప్టిక్స్ లో అంటే ఏమైనా ప్రాపర్టీస్, ఆప్టికల్ ప్రాపర్టీస్ అట్లాంటి ఏమైనా చేయడానికి ఇటువంటి ఇట్లా కొంచెం ఇంట్రెస్టింగ్ ఉండేది సార్. ఇంకోటి సార్, టెరాహైడ్స్ లోపల ఏమైనా వస్తాయి సార్ దీనికి ఫీచర్లు? అంటే టెరాహైడ్స్ అంటే ఫారెన్ ఫ్లడ్ సార్. ఫారెన్ ఫ్లడ్ అంటే ఇప్పుడు సమ్ 30 మైక్రోమీటర్ నుంచి 1 మిల్లీమీటర్ ఆ రేంజ్ లో వేవ్లెన్స్ లో ఉండేటువంటి వాటికి ఏమైనా రెజొనెన్సెస్ అట్లాంటివి ఏమైనా వచ్చే అవకాశం ఉంటుందంటారా సార్ వీటికి?
చూడొచ్చు, స్టడీ చేయొచ్చు.
అదే సార్, అంటే అదే మీరు కనుక ఒకవేళ చేసేస్తే ఇట్లా నేను అంటే నాకు తెలిసి కూడా హైదరాబాద్ లో ఉన్నాయి సార్ ఇవి టెరాహైడ్స్ స్పెక్ట్రోమీటర్లు. వాటిలో